Okay, team 5, you're on. I'm going to mute my microphone, okay?
Hello, thank you so much for taking the time to watch our presentation. We appreciate it, and we're very excited to share a senior design project with you. My name is Nick. I'm here with Ryan, Yona, and Sarin, and we have designed a haptic glove for virtual reality interface. So what does that mean? It means you put on our glove, put on an Oculus, and you can touch and feel things inside a virtual world. Now, why did we decide to build this? Well, virtual reality, companies like Oculus, Magic Leap have made tremendous strides in recent years in auditory and visual perception. Right? You can see and hear things that you couldn't imagine several years ago. But the one area where that experience has been lacking is in touch feedback. So right now, if you're, say, doing a job training, simulation, or a video game, you're expected to interact with things in this virtual world with your hands. But the lack of touch feedback completely breaks that immersive experience. And that is the void that our product is trying to fill. And this isn't just an interesting technical problem, but it's also a fantastic business opportunity. Virtual reality has seen explosive growth in the past several years. And the virtual reality haptics subset of that market is an estimated $1.5 billion. So this is an extremely exciting technical project to work on, but it's also a very lucrative. Now I'm going to pass it on to Yona to talk about some of the existing solutions.
Yeah, so the current state of the market is there are products that range from inexpensive but really poor quality all the way to more theoretical projects that are still in a lab that aren't commercially available. Our goal with our project was to sort of bridge that gap and try to create a glove that looks a little bit more like something on the right, but also a little bit more like something that you can see on the left. So our glove, thanks. So our glove is lightweight and inexpensive. So it weighs only 100 grams and it costs under $50 to make. It incorporates both structural and tactile feedback. So if you look at the glove on the right, you can see that the electrostatic clutch, that metal plate you see going over the finger, is the structural feedback that mimics something you'd feel when you grip something. And there's also tactile feedback, which is vibrations that mimic the sense of touch. And Soren's going to talk a little bit more now about what the technology looks like and how that actually comes together.
Yeah, so there's three main subsystems to our technology. The first is the tactile feedback, which is light sensations of touch, similar to pushing buttons or pressing onto a tabletop. We accomplish this through piezoelectric actuators, which are simply vibration motors, similar to those found in your phone. However, the second component to our project and the technology is the structural force feedback. This is holding a ball or another object and actually feeling the force pushing back on your hand, stopping your hand from closing. We accomplish this through an innovation called an electrostatic clutch, which we'll dive into deeper in a second. But this is really the core of our technology and what makes all this possible in a lighter, more streamlined form factor and at a lower cost. And then lastly, we package all of these hardware components together with an innovative software system using the Oculus Quest and their hand tracking system. But we built our own Unity and Arduino software environment around that to package everything together, make sure the signals flow, and have a seamless user experience. So now for the electrostatic clutch design, what this really is at its core is two metal plates with a dielectric in between, essentially a capacitor. When the metal electrodes have a charge on them, a voltage is applied, they stick together and cause a frictional force on the back of your hand and restrict your finger from moving. However, when no voltage is applied, your finger is free and able to move freely. And as you can see, the force restriction specifically is proportional to 1 over the thickness of the dielectric squared. Hence, getting that thickness down as much as possible is critical. So we ended up choosing a 0.5 micrometer thick mylar film to do this, which is incredibly thin and works perfectly for our purpose, except for the fact that it's pretty fragile. So we had to apply a carbon nanotube layer on top of the dielectric to keep the thin form factor, but still make it much more structurally sound. Using these carbon nanotubes was really what we were able to get the electrostatic clutch to actually work for our haptic glove.
So now I'll talk about some of the design specifications of our glove and some of the constraints we had in the design process. So we were able to achieve a 10 Newton stopping force per finger on the structural haptic feedback. This 10 Newtons is enough to stop your finger from closing, but not too much such that it puts your finger in any danger. Some of the more experimental gloves on the market through their testing have had incidents where they break someone's finger because the force is too high, but our stopping force is a perfect 10 newtons. The other stat I wanted to bring to your attention is our low latency of 100 to 150 milliseconds. So the human brain can't perceive a lag of less than 300 milliseconds. So the lag between our visual and haptic feedback is so low that you can't perceive it. And we're able to achieve this through our piezoelectric actuators. In terms of safety, our time spent on material selection allowed us to have a maximum voltage of 25 volts and maximum current of 1 milliamp. So this makes the glove safe for users. And one constraint that we had in the design process was that we had a break area of only 5 centimeters squared. So this is the size of your finger. If we had a larger break area to work with, it would have been easier to make an electrostatic clutch, but we had the constraint of the size of the hand. So we were able to work around that. So now to talk about some engineering standards. The ISO sets most of the standards for haptic human interfaces. So they set standards on the ergonomics of the glove to make sure it's safe for you to use for extended periods of time, and also how you test the glove. So our glove currently meets all the ergonomic standards, but future work will require us to do more significant testing to make sure our glove is resilient under a wide variety of circumstances. We were cut short on our testing process due to the current health crisis. So other standards that we were mindful of were the ASTM's material standards. So there are standards for silver coating on steel conductors. In our electrostatic clutch, we use silver epoxy as a conductive over our steel plates. Our silver epoxy thickness is well within the range of the ASTM. And in terms of testing for carbon nanotubes, in our preliminary tests, the carbon nanotubes look resilient, but we will require future work with significant lab-based testing to make sure our carbon nanotubes are compliant before we deliver any product to market. The IEEE still also sets standards for electrostatic discharge that our glove is well within the range of. So thanks so much for taking the time to watch our presentation, and we look forward to answering any questions you guys may have.